Module 3 is the final module of the chapter Hypergeometric function. We have started with the hypergeometric equation and its solution gives the hypergeometric series. With a simple substitution, we have seen that the hypergeometric equation can be converted into a confluent hypergeometric equation. We have also studied its solution. We have also looked into the differentiation and the integral representation of the hypergeometric series as well as confluent hypergeometric series. In this module 3, we will look into 7 very different examples which will clear this chapter of hypergeometric function. This module consists of 7 examples of the hypergeometric function. In example 1, we have to show 1 minus x to the power minus alpha is equal to f of alpha beta beta x. Now, from the definition of hypergeometric function given in equation 1, we get f of alpha beta gamma x is equal to 1 plus alpha dot beta by gamma into x by 1 factorial plus alpha into alpha plus 1 beta into beta plus 1 divided by gamma into gamma plus 1 dot x square by 2 factorial plus dot dot dot. Since in our right hand side we have to show f alpha beta beta x, we will replace this gamma by beta in equation 1. And if you do that, we put beta equal to gamma, we will get f alpha beta beta x is equal to 1 plus alpha dot beta by beta into x by 1 factorial plus alpha into alpha plus 1 beta into beta plus 1 divided by beta into beta plus 1 dot x square by 2 factorial plus dot dot dot. Then you simplify this expression, this beta will cancel with this beta into beta plus 1 will cancel with beta into beta plus 1 and so on, and you will get the simplified expression as f alpha beta beta x is equal to 1 plus alpha into x by 1 factorial plus alpha into alpha plus 1 into x square by 2 factorial plus alpha into alpha plus 1 into alpha plus 2 into x cube by 3 factorial plus dot dot dot. We further simplify it to bring the result, and in the next step we write alpha into x by 1 factorial as minus alpha into minus x, so that their product remains plus alpha x. In the similar manner, the next term alpha into alpha plus 1 is written as minus alpha into minus alpha minus 1 divided by 2 factorial, which is already present here, such that the product of minus alpha into minus alpha minus 1 is actually alpha into alpha plus 1, because both the negative sign gives the positive sign. Similarly, you get the third term, and this is nothing but the expansion of the binomial 1 minus x to the power minus alpha, which is our required result. In example 2, we have to show log 1 plus x to the base e is equal to x into f 1 1 2 minus x. From the definition of hypergeometric function, we get, as given in equation 2, f of alpha beta gamma x is equal to 1 plus alpha dot beta by gamma into x by 1 factorial plus alpha into alpha plus 1 beta into beta plus 1 divided by gamma into gamma plus 1 into x square by 2 factorial plus dot dot dot. Now, as you can see, the right hand side we have to prove x into f of 1 1 2 minus x, and this gives us the hint that we have to replace alpha by 1, beta by 1, gamma by 2 and x by minus x. and this is exactly what we do, and we substitute alpha equal to 1, beta equal to 1, gamma equal to 2, and we replace x by minus x in equation 2. And if you do that, you will get f of 1, 1, 2 minus x is equal to 1 plus 1 dot 1 divided by 2 into minus x by 1 factorial plus 1 dot 2 into 1 dot 2 divided by 2 dot 3 into minus x square divided by 2 factorial plus 1 dot 2 dot 3 into 1 dot 2 dot 3 divided by 2 dot 3 dot 4 into minus x whole cube divided by 3 factorial plus dot dot dot. We multiply both sides by x because the right hand side of the function f is multiplied by x, and if you do that, you will be getting x f 1 1 2 minus x is equal to x minus x square by 2 plus x cube by 3 minus x to the power 4 by 4 plus dot dot dot, and which is nothing but the expansion of log 1 plus x to the base e. Hence, we have shown that log 1 plus x to the base e is equal to x into f 1 1 2 minus x, which is our required result. In example 3, we have to show tan inverse x is equal to x of f half 1 3 by 2 minus x square. Just like the previous examples, we will start with the definition of hypergeometric function, which is given in equation 3, that is f alpha beta gamma x is equal to 1 plus alpha dot beta by gamma into x by 1 factorial plus alpha into alpha plus 1 beta into beta plus 1 divided by gamma into gamma plus 1 into x square by 2 factorial plus dot dot dot. Since the right hand side have the function f of half 1 3 by 2 and minus x square, we will be replacing this alpha by half, beta by 1, gamma by 3 by 2 and x by minus x square. Therefore, we put alpha equal to half, beta equal to 1, gamma equal to 3 by 2, and we replace x by minus x square in equation 3, and we will get f of half 1 3 by 2 minus x square is equal to 1 plus half into 1 divided by 3 by 2 into minus x square by 1 factorial plus half into 3 by 2 divided by 3 by 2 into 5 by 2 into 1 dot 2 into minus x square whole square divided by 2 factorial and so on. If you simplify the right hand side, you will be getting 1 minus x square by 3 plus x to the power 4 by 5 minus dot dot dot. Since the right hand side has the expression x into f, we will multiply both sides with respect by x, and we will get x into f half 1 3 by 2 minus x square is equal to x minus x cube by 3 plus x to the power 5 by 5 minus dot 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 is equal to tan inverse x, which is our required result. In the last 3 examples, we have seen how to get results by using various values of alpha, beta, gamma of the hypergeometric function. In the coming examples, we will look into the differentiation and integration of the hypergeometric function, examples involving those properties. In this example, we have to show ddx of f alpha beta gamma x is equal to alpha by beta f of alpha plus 1, beta plus 1, gamma plus 1 x. And after that, we have to deduce the nth derivative of f alpha beta gamma x is equal to alpha suffix n beta suffix n divided by gamma suffix n into f of alpha plus n, beta plus n, gamma plus n into x, where alpha suffix n is the Pochhammer's symbol. And in the second part, we have to find the expression when the value of x is equal to 0. We start with the definition of the hypergeometric function, which is f of alpha, beta, gamma x is equal to 1 plus alpha dot beta by gamma into x by 1 factorial plus alpha into alpha plus 1, beta into beta plus 1 divided by gamma into gamma plus 1 into x square by 2 factorial plus alpha into alpha plus 1 into alpha plus 2, beta into beta plus 1 plus beta plus 2 divided by gamma into gamma plus 1 into gamma plus 2 into x cube by 3 factorial plus dot dot dot. We differentiate both sides with respect to x, and we will get d dx of f equal to alpha into beta by gamma plus alpha into alpha plus 1, beta into beta plus 1 divided by gamma into gamma plus 1 into x by 1 factorial, alpha into alpha plus 1 into alpha plus 2, beta into beta plus 1 into beta plus 2 divided by gamma into gamma plus 1 into gamma plus 2 into x square by 2 factorial plus dot dot dot. We take alpha beta by gamma common from all these terms, and we will be getting alpha beta by gamma multiplied by 1 plus alpha plus 1 beta plus 1 divided by gamma plus 1 into x by 1 factorial, alpha plus 1 alpha plus 2 beta plus 1 beta plus 2 divided by gamma plus 1 into gamma plus 2 into x square by 2 factorial plus dot dot dot, and which is equal to alpha by beta f of alpha plus 1 beta plus 1 gamma plus 1 into x, which is our required result. We now have to show that the nth derivative of f alpha beta gamma x is equal to alpha suffix n beta suffix n gamma suffix n into f of alpha plus n beta plus n gamma plus n x. To prove this, we will use the principle of mathematical induction, which means that we have to prove the result first for n equal to 1, then we have to assume that the result is true for n equal to m, and assuming that, we will next have to prove that the result is true for all n equal to m plus 1, where m are integers. So, we use the principle of mathematical induction. Here we observe that for n equal to 1, if you substitute n equal to 1 in equation 4, you will get equation 5, which is d dx of f of alpha beta gamma x is equal to alpha by beta f of alpha plus 1 beta plus 1 gamma plus 1 into x. And this is exactly what we have proved in the first half of the problem, that is d dx of f is equal to alpha by beta f of alpha plus 1 beta plus 1 gamma plus 1 x. Hence, we can say that this result 4 is true for n equal to 1. Next, we assume that the result 4 is true for n equal to m, where m is any integer, any positive integer. That is, we are assuming that the mth derivative of f alpha beta gamma x is equal to alpha suffix m beta suffix m divided by gamma suffix m f of alpha plus m beta plus m gamma plus m x, where alpha suffix m is Pochhammer's symbol, which we have stated earlier. This is given by equation 6. We next differentiate 6 both sides with respect to x once, and if you do that, we will get the m plus 1th derivative of f alpha beta gamma x is equal to alpha suffix m beta suffix m divided by gamma suffix m d dx of f alpha plus m, beta plus m, gamma plus m x. And if we simplify this, we will get the expression is equal to alpha suffix m, beta suffix m divided by gamma suffix m into alpha plus m, beta plus m divided by gamma plus m into f of alpha plus m plus 1, beta plus m plus 1, gamma plus m plus 1 x, which we get using the expression 5. Now, please note that ddx of f is equal to alpha by beta f of alpha plus 1, beta plus 1, gamma plus 1 x. That is, if here it is alpha, here it is replaced by alpha plus 1. So, if here it is alpha plus m, like in this expression, this is going to replace by alpha plus m plus 1. This is exactly what we have done here. Therefore, the m plus 1th derivative of f alpha beta gamma x is equal to alpha m plus 1 beta suffix m plus 1 divided by gamma suffix m plus 1 into f of alpha plus m plus 1, beta plus m plus 1, gamma plus m plus 1 into x. Therefore, assuming the given equation is true for n equal to m, we have proved that it is true for n equal to m plus 1, and hence by the principle of mathematical induction we conclude that equation 4 is true for all positive integer n. Therefore, the nth derivative of f alpha beta gamma x is equal to alpha suffix n beta suffix n divided by gamma suffix n f of alpha plus n, beta plus n, gamma plus n x. For the third part of the problem, we have to substitute x equal to 0 to calculate the value of nth derivative of f alpha beta gamma 0. We put x equal to 0 in the expression and we will get the nth derivative of f alpha beta gamma 0 is equal to alpha suffix n beta suffix n divided by gamma suffix n into f of alpha plus n beta plus n gamma plus n 0, which is equal to alpha suffix n beta suffix n divided by gamma suffix n into summation r equal to 0 to infinity alpha plus n suffix r beta plus n suffix r divided by gamma plus n suffix r into x to the power r by r factorial. The first expression, if you put r equal to 0, you will get this is equal to alpha plus n 0, beta plus n suffix 0, gamma plus n suffix 0, and all these values are 1. For r equal to 0, x to the power 0 by 0 factorial, this is also equal to 1. For r equal to 1, 2, 3 dot dot dot, all the expression will contain x, and hence if you put x equal to 0, all these expressions will be equal to 0 except the first one whose value is 1, and hence the answer is alpha suffix n into beta suffix n divided by gamma suffix n, which is our required result. In this example, we have to show that p n x, which is the Legendre's polynomial of degree n, is equal to f of minus n n plus 1 1 into 1 minus x by 2. Now, please recall the Rodricks formula, which says that p n x, that is the Legendre's polynomial of degree n, is equal to 1 by n factorial 2 to the power n into nth derivative of x square minus 1 whole to the power n. Now, we take this minus sign common, and this whole expression is rewritten as minus 1 whole to the power n divided by n factorial 2 to the power n into the nth derivative of 1 minus x square whole to the power n. We write 1 minus x square as 1 plus x into 1 minus x, and then we get the next line as minus 1 whole to the power n by n factorial the nth derivative of 1 minus x whole to the power n into 1 plus x whole to the power n divided by 2 factorial, which can be rewritten as minus 1 whole to the power n divided by n factorial the nth derivative of 1 minus x whole to the power n into 1 minus x by 2 whole to the power n, which can be written as minus 1 whole to the power n divided by n factorial the nth derivative of 1 minus x whole to the power n multiplied by 1 minus n into 1 minus x by 2 plus n into n minus 1 by 2 factorial 1 minus x by 2 whole square minus dot dot dot, where we use the binomial expansion. We next multiply this whole expression by 1 minus x whole to the power n, and we will get minus 1 whole to the power n divided by n factorial the nth derivative of 1 minus x whole to the power n minus n by 2 1 minus x whole to the power n plus 1 plus n into n minus 1 divided by 2 factorial into 2 square multiplied by 1 minus x into n plus 2 plus dot dot dot. Now, taking the nth derivative, where we use the formula the nth derivative of a minus bx whole to the power m is equal to minus 1 whole to the power m b to the power n m factorial by m minus n factorial into a minus bx whole to the power m minus n. We will get, please note here n remains the same, whereas your m is in this case n, in this case n plus 1, in this case n plus 2 and so on. So, if you use this formula, you will get after the nth derivative minus 1 whole to the power n divided by n factorial multiplied by minus 1 whole to the power n into n factorial minus 1 whole to the power n into n by 2 into n plus 1 factorial by 1 factorial into 1 minus x plus minus 1 whole to the power n into n minus 1 into n minus 2 divided by 2 factorial 2 square into 2 factorial 1 minus x whole square minus dot dot dot. On further simplification, this can be written as 1 plus minus n into n plus 1 divided by 1 into 1 factorial 1 minus x by 2 plus minus n into minus n plus 1 into n plus 1 into n plus 2 divided by 2 dot 1 into 2 factorial 1 minus x by 2 whole square plus dot dot dot, and this is by definition f of minus n n plus 1 1 minus x by 2, and hence we prove that p n x, that is the Legendre's polynomial of degree n, is equal to f of minus n n plus 1 1 minus x by 2. In this example, we have to show f of alpha beta gamma x is equal to 1 minus x to the power minus alpha f of alpha gamma minus beta gamma into minus x by x minus 1, provided mod x is less than 1 and x by 1 minus x modulus of that is also less than 1. Please recall the integral representation for the hypergeometric function, which gives f of alpha beta gamma x is equal to gamma function gamma divided by gamma function beta, gamma function gamma minus beta, integration 0 to 1 t to the power beta minus 1 1 minus t to the power gamma minus beta minus 1 1 minus x t to the power minus alpha dt. We substitute u equal to 1 minus t and we get gamma function gamma divided by gamma function beta into gamma function gamma minus beta, integration 0 to 1 1 minus u to the power beta minus 1 u to the power alpha minus beta minus 1 1 minus x plus x u to the power minus alpha into minus du. Further simplification gives f of alpha, beta, gamma x is equal to 1 minus x to the power minus alpha gamma function gamma divided by gamma function beta gamma minus beta integration 0 to 1 u to the power gamma minus beta minus 1 minus u to the power beta minus 1 into 1 minus x by 1 minus x u whole to the power minus alpha du given by equation 8. We replace beta by gamma minus beta and x by x minus 1 in equation 7, and we will get f of alpha gamma minus beta gamma x by x minus 1 is equal to gamma function gamma divided by gamma function gamma minus beta gamma function beta integration 0 to 1 u to the power gamma minus beta minus 1 minus u to the power beta minus 1 multiplied by 1 minus x by x minus 1 u whole to the power minus alpha du given by equation 9. Now, if you compare equation 9, especially the right hand side, with equation 8, the right hand side, you will see both these expressions are same, and hence we conclude using 8 and 9 that f of alpha beta gamma x is equal to 1 minus x to the power minus alpha f of alpha gamma minus beta gamma x by x minus 1. Summing up, in this chapter we have learned about hypergeometric function. We have started with the differential equation of the hypergeometric equation whose solution is the hypergeometric series. We have also learned about confluent hypergeometric function and the confluent hypergeometric equation, along with the differentiation and the integral representation. We end this chapter with some good examples which will easy to understand the hypergeometric function. I hope it is clear to you. Thank you.